Hello friends, this is lecture 3 of electricity and magnetism for BSc and MSc students. So here we're gonna learn how to apply Gauss law that we have already discussed how to prove Gauss law in the last lecture. Link is given in the description box. So here we're gonna learn how to apply the Gauss law to find electric field or electric field intensity due to a uniformly charged spherical cell, right? So today we're gonna discuss about only electric field intensity due to a uniformly charged spherical cell. In the next lecture we're gonna discuss the electric field intensity due to uniformly charged solid sphere, okay? And also electric field intensity due to infinitely charged uniformly charged infinite sheet, okay? So we will get you will get 2 or 3 lectures on the applications of Gauss laws, okay? Because I'm not going to cover all these 3 or 4 topics in the same video because it will be very long, okay? So before we start, please subscribe the channel, and if you think these videos are helpful, please share with your friends, hit the thumbs up button, and inspire me to create new videos for you. So subscribe the channel, also hit the bell icon so that you get notified when new lecture will be uploaded. So now let's start. Suppose we have a spherical cell, okay? Suppose we have a spherical cell. So this is a spherical cell of radius capital R. Its radius is capital R, and it is uniformly charged, okay? Q amount of charge is uniformly distributed over its surface. Let us assume that way. So Q amount of charge is distributed over the surface of this spherical cell, and its center be O and its radius be capital R. Now let us consider a point P here outside the cell for the first case. Outside the cell, which is at a distance of small r, which is at a distance of small r from the center of this spherical cell. And let us also assume a spherical Gaussian surface through this point P. So this is the point P, suppose. So let me write here P. So this is the point P. So we have assumed another solid sphere which will be called Gaussian surface. So let me use dotted line to draw this Gaussian surface. So this is the Gaussian surface, and its radius will be this small r, which is the distance between the P and O, right? Small r. So now you see, we will calculate here electric field intensity due to this spherical cell, uniformly charged spherical cell at P. When P is outside the cell, that means R greater than capital R, small r greater than capital R. This is the first case. And next case, if P is on the surface of this cell, and when P is inside the cell. In all the 3 cases, we're gonna calculate electric field intensity, right, due to this spherical cell. So let me write what we have considered here. So Q amount of charge is distributed uniformly on the surface of the spherical cell of of radius capital R, and here we are to calculate the electric field intensity due to this cell at the point P, right? At the point P, which is at a distance of small r from the center O of the cell, right? So here small r is greater than capital R. Now let us consider a very small surface element. This is, suppose its area is suppose ds. Its area is suppose ds, and here you see. So let me write the P here. This is the P, suppose. Now the direction of the electric field will be along the distance r, which will be outward. If the cell is positively charged, so it will be radially outward, because we know that direction of electric field lines is radially outward from the positive charge, right? So it should be radially outward from the sphere. So this is the direction of the electric field, right? This is the direction of the electric field. And we know that area vector, suppose this is a surface, so the direction of the area vector, that should be normal to this surface, right? Okay, so for this small area element ds, so unit vector along the, so here this will be the ds, the area vector will be represented. Let me write here, let me represent the area vector by ds vector. So this is ds vector, right? And which will be normal to this area element ds, this is small area element ds. So hope you have understood these things. So now, so let me go to another slide here. Let me draw the diagram again. Just okay. So let me draw it properly. Okay. So this is the direction of electric field E, and the area vector is represented by ds vector. Okay, so let me consider that way, right? So here E be the electric field at P, and ds is the area vector. It is vector normal to the area, to the small area element. ds, right? So let me assume that way. So then, according to Gauss theorem, okay, according to Gauss theorem, so according to Gauss theorem, electric flux, which is given by integration E vector dot ds vector, which is according to Gauss theorem, that should be 1 by epsilon naught times of q, which is the charged enclosed by this Gaussian surface, right? So now you see, integration dot product of two vectors E and ds, that will be E ds cos theta, right? Q by epsilon naught. Now you see here, the theta is the angle between E and ds, E vector and ds vector, that will be 0 in this case, right? So here let me write here, angle between, just wait, let me write here one more step, EDS, if theta is equal to 0, then cos 0 is 1, so we can write EDS, integration EDS q by epsilon naught. So here we're gonna write, since angle between E vector and ds vector is theta is equal to 0, theta is equal to 0 degree, and cos 0 degree is 1. That is why we have got this integration EDS, right? this cos theta becomes 1, right? So here you see, from the diagram it is very clear that this E vector and ds vector are in the same direction along the same line, so angle must be 0. So now let me go to the next slide. Before that, let me copy this last step so I can continue. So here you see, so this is the last step we have got, and also let me take the diagram as well. So this is the figure, let me draw it here again. So this is the figure, right? So here you can see this can be written here, electric field is constant, so it can be taken outside the integral, right? So here we can say that E integration ds will be equal to q by epsilon naught. Now you see, if you integrate ds, this is surface integral, right? S, let me write here, S surface integral. So let me write S here. So surface integral. If we integrate ds, you find the surface integral, that's gonna give you the surface area of this Gaussian surface, which is spherical. So, and its radius is smaller, so its area must be 4 pi r square. So if you use this value here, E 4 pi r square is equal to q by epsilon naught, then your E will be equal to the electric field at P, that will be given by 1 by 4 pi epsilon naught into q by r square, right? Into q by r square. So this is the electric field. This is what? Electric field at P due to the cell, right? Now you see, in vector form, if you want to write in vector form, then you can write vector E is equal to 1 by 4 pi epsilon naught q by r square n cap. So what is n cap here? So n cap is the unit vector along ds, right? If we assume that unit vector along ds is suppose n cap, so n cap unit vector along ds vector, right? So if you imagine that this is the vector form, okay? So hope you have understood this. Now let us consider this point is suppose on the surface of this cell, not outside the cell. That means in this case, case 2, if P is on the surface of the cell, that means small r is equal to capital R. So in that case, let me draw the diagram here. So this is the charged sphere, right? It's uniformly charged sphere, and its radius is capital R, and the point P is on its surface, right? And now small r is equal to capital R. In that case, so here we have got electric field. So let me copy these things. Wait. So now let me write here. So as you can see, as we have taken here, small r is equal to capital R. So here replace the small r by capital R. Capital R square. Here also capital R square. So hope you have understood this. So now case 3. If P is inside the cell, that means small r is less than capital R. In that case, as charge inside the cell Q is equal to 0. So here electric field E will be also equal to 0, right? Because the Q amount of charge Q is distributed over the surface of this sphere only, not within the not inside the sphere. So hope you have understood. That's why inside the sphere, spherical cell, not solid cell, spherical cell, that means hollow sphere, it will be 0. So hope you have understood this. Then in the next video we're going to discuss how to find the electric field intensity at a point due to a solid sphere, okay, uniformly charged solid sphere. So in that case also we will get 3 cases, okay. We're gonna discuss that one in the next lecture number 4. So that will be appear at the end of the screen when that video will be uploaded, okay. So check the end screen. If it is already uploaded, then it will appear, otherwise not, okay. So thank you for watching. See you in the next video.